guys. Uh, all right. Have we successfully fixed all of the AV? Like,
Yeah.
is the Zoom screen share and everything working?
Just also maybe have your microphone a little larger.
Cool. Can you guys hear me? Amazing. Okay. Well, thank you all for being here. Thanks, Butcher and Charlie, for having us. Today, we're going to tell you about building computational models of social cognition in Memo. Possibly we should start by telling you who we are. Um, Leo, what have I done wrong? Help.
World.
Well,
Do you want to just use that?
yeah, I think I do want to just use that. All right. Well, okay. That didn't do what I expected it to do. Uh, what if what if we just started over? Hi guys, I'm Kartik. Today, Leo and I are going to tell you about building computational models of social cognition in Memo, but perhaps we should start by telling you who we are. Oh my gosh. Uh, uh, right. I'm Kartik. I'm a grad student at MIT. I work on programming languages for theory of mind. Leo, would you like to introduce yourself?
Uh, sure, yeah. As Charlie just said, I'm a postdoc at Stanford. I just finished my PhD at MIT as well. I was also in Josh Shedamam's group, which is how I know Kartik. I primarily work on language. I'm really interested in storytelling these days. So if you're interested in that, come find me. And I'm super excited about these kinds of computational models that we'll be talking about today, because I think that one of the really cool aspects, as we'll hopefully see, is that they provide formal ways to computationally model concepts that really look a lot like the kinds of words that we use in language. And so one of the things that I hope that I'll get to discuss with all of you guys today is how we can take these kinds of computational models and capture more of, I think, what in these kinds of words that we're trying to make little steps towards formalizing, you feel like is not captured. I think like every model is kind of just a small approximation to the human mind in some way, but also I think one of the really good things that you can get out of a computational model is like some new interesting way that the math actually sheds light on something that feels really intuitive. And so that's, I think, what we're hoping you'll take away from this, regardless of where you fall in this space.
Okay, cool. So here's what we're going to do in the next 90 minutes. I'm going to spend about 45, let's hope for 40 minutes telling you what Memo is, why you might possibly consider using it, what you could use it for, what it looks like to use Memo, and I'm going to go kind of fast. This is going to be like a perceptual feature-based, like vibes-based introduction to Memo. Then we're going to pause for a break, like a 5-minute break, like quick break, while we change over. And then in the rest of the time, Leo is going to do an in-depth deep dive on how to use Memo. Leo's going to actually live code some models on this computer in front of you. And we've set it up so that you guys can actually follow along on your computer. So we set up these Google Colab notebooks that are exactly the same as what Leo's going to present, and you can run them live and kind of tinker and play around. And hopefully that will give you a way to like play and learn and have a lot of fun while doing so. Okay, that's the plan for today. But I wanted to start by telling you a little bit about what kinds of models you can use Memo for. And you know, I was thinking about how to start this, and then I was watching the tutorial yesterday and seeing these slides that Charlie and Watari were presenting about teaching and theory of mind, and I thought that might be a good place to start. So I'm going to start by playing this little game with you guys, a game that's about communication or teaching. And here's how the game works. You're at a table, and there's these three things at the table. There's a pink circle, a green circle, and a green square. And across from the table is your partner, who is randomly assigned one of these three objects to teach you or to communicate to you. But what makes this game kind of fun or interesting is that your partner is very limited in what they're allowed to say or how they're allowed to communicate with you. Your partner can only use one of four words. They can either say round, green, square, or pink. Okay, so let's practice. Suppose your partner says, can you please bring me the square one? Can you guys just like point for me which object would you pick? Okay, great, amazing, strong preference for the green square. Right, if your partner says, can you please bring me the pink one? Okay, can you guys like point for me? Amazing, strong preference for the pink circle. But what if your partner says, can you please bring me the green one? This one's harder because there are two things that are green. The green circle and the green square are both green. But perhaps surprisingly to you, or perhaps not, people tend to have a preference between these two objects. People tend to prefer the green circle over the green square. And this is a real phenomenon. It's replicable. Here's some data from Ching and Franca in 2015, where they found that twice as many people pick the green circle over the green square. Okay, raise your hand if you've seen this game before. Raise your hand if you know why people have this preference. Okay, don't spoil it for everyone else. I'm gonna try to offer you one account of why people prefer this green circle over the green square, like one account of what's breaking the symmetry between these two green shapes. Okay, and here's the account. The account says, well, let's think about this little game like actually as a game, in the sense that, you know, when you play a game, you can play it at two levels. You could either play it at the literal level of I'm just trying to make a move that follows the rules, or you could play as a more sophisticated strategic player where you think about what your partner or your opponent in the game would do, and then think about how you would appropriately respond to that. So there's like a bit of recursive reasoning involved. So let's try to do that analysis for this game. So suppose I'm the listener and I hear my partner say green. Well, what do? As we just discussed, like I'm kind of stuck, right? Like I don't know which of these two objects my partner means because they're both green. But what if I think about what my partner might be thinking? Well, suppose my partner actually is trying to communicate the green circle. What can she do? Well, she could say green, but that's ambiguous. Or she could say round, but that's actually also ambiguous. So in some sense, my partner has the same problem I do, which is that she's forced to choose between these two bad alternatives. Okay, but let's keep going. My partner is also perhaps strategic, and she might think about how I might be thinking about this game recursively. And she actually then has this interesting move available to her. She can do the following reasoning. She can say, look, Kartik knows that if I were trying to communicate the green square, then I would never say green. I would say square, because square is unambiguous, right? Like if I said square, Kartik would definitely pick the green square. You guys all pointed to the green square when I said square. So if that's the case, then if I say green, what should Kartik think? Well, he should think the only reason I picked this risky, ambiguous utterance, the word green, instead of the word square, is if I didn't mean the green square, but I meant the green circle. And so Kartik would infer that I meant to communicate or meant to teach the green circle rather than the green square. Does that scan for everyone? Does the reasoning go through? Okay, if it doesn't, now's a good time to ask a question. Okay, cool. I'm going to keep going then. So this way of reasoning about how words come to acquire meanings is called the Rational Speech Acts framework. And it's been really, really influential in our research community, the like computational linguistics or psycholinguistics research community. And one reason it's been so successful is that if you build a computational model of this kind of reasoning, if you actually write out the equations for how these two players in this game should play, and you make predictions, it very beautifully and very precisely captures variance in people's responses, like really, really precisely. And that suggests that maybe it really is capturing something about how people are playing this game. But it's actually not just linguistics. This type of reasoning about how people reason about other people in terms of recursive social reasoning or thinking about thinking is really all over the place in our broader discipline, not just in linguistics, but also in all of these other fields like moral psychology and computational psychiatry, theory of mind and mental state inference, studying how we cooperate or compete, studying emotions. Lio and I talked about that yesterday, pedagogy and education, responsibility attribution. Sarah is somewhere in the audience. She worked on that and did some really amazing work. And actually, like about 30 minutes ago, we saw a slide on like cognitive hierarchy theory, which to me is also like closely philosophically, thematically related. So I would offer to you or propose to you that what we're looking at is actually like this whole programming paradigm, this whole paradigm of building computational models. And actually, Fiery Cushman just wrote this review paper that broadly discusses what the themes and motifs of this paradigm are around modeling people as recursively reasoning about each other. Okay. So I, during my PhD, feel like I've been really lucky to get to talk to and work with a lot of people who work on this modeling paradigm across all of these different subdisciplines of cognitive science and linguistics. And it's been a lot of fun, and I've learned quite a lot. But one thing I've learned is that building these models is not easy. It's actually kind of hard. And actually, I would like to take a survey. So raise your hand if you've ever built one of these kinds of models, one of these recursive reasoning models. Okay, keep your hand up if it was kind of hard. Like, was it kind of hard? Yeah, okay, so if you look around, you'll see at least some people endorse the sentiment that writing these kinds of models is kind of hard. And I would like to spend approximately 2 minutes, maybe like 4 minutes, trying to convince you of why exactly it's hard. So just to get you thinking, just to get you kind of introspecting about what might make it difficult for us to reason about and write down computational models of this kind of reasoning, I want you to watch this little video clip. And as you watch it, like firstly, just be entertained, but also start thinking about like, what is it about this situation that makes it so hard or so tricky to think about? Here's the video clip.
Joey, they know that we know.
Oh,
Joe.
they know you know.
I would say, thank God, everybody knows it's finally over, but that hasn't been working for me.
Can't believe those two. They thought that they could mess with us and mess with us. Oh. Don't know that we know they know we know. Joe, you can't say anything.
If I wanted to.
Okay, so as a programming languages researcher, when I watch that clip, I get this like strong sense that the reason thinking about this kind of recursive reasoning is difficult is actually the same reason that doing anything at all with a computer is difficult, which is that it's hard to do it correctly and it's hard to do it efficiently. So let me explain what I mean by that. So here's what I think the problem with implementing these models correctly is. The problem is actually closely related to what Lio was just saying. It's that when we think about other people's thinking, we marshal this like very, I don't know, beautiful, rich, large vocabulary of words like believe, think, see, do, know, want, imagine. But when we're building a Bayesian model, when we're actually writing code, the verbs we get to use are verbs like sample a random variable, do inference, or condition a distribution. And so in our heads, we always are translating between believe, think, see, do, know, want, imagine to things like sample, infer, and condition. And how do you know if the semantics of that translation are preserved? Well, you don't. You just have to trust yourself. And if you make a mistake, which is actually really easy. In fact, I make these mistakes all the time, and I've been doing this for many years now. You end up with all kinds of really subtle and tricky bugs. Bugs like having an agent who somehow like secretly has mind control over another agent because there's some leakage of probability because you aren't quite conditioning over the right random variable, or there's some dependency structure that you miss. It's really messy. And I think that's what makes it really hard. It's this translation between believe, think, see, do, know, want, imagine to sample, infer, condition. Okay, the problem with efficiency is that when you're thinking about other people's thinking, there's this kind of combinatorial explosion of possible worlds you have to keep straight. There's like the real world, which has all of its real possibilities, but then there's also the imagined worlds that people you're imagining might be imagining. And then there's the imagined worlds that people you're imagining other people might be imagining. And this rapidly starts getting out of hand. And so the upshot of this is that in practice, if you walk around a bunch of cognitive science or social psychology labs and you ask people like, well, how long does it take you to run your model? How long does it take you to fit your model? You get answers that range on the order of like minutes to hours to even like many days on like a computer cluster. And I think this makes doing this kind of science like fundamentally a lot harder than it than it needs to be. Because if you're a grad student and you're working on a project and it takes you 3 days of compute to test your hypothesis because it takes you 3 days of compute to fit your model, then I think you just think about science in a totally different way than if it takes you, let's say, a second or a millisecond to fit your model to data. Okay, so these are the two problems, I think, correctness and efficiency. And all of this was kind of swimming around in my head around this time last year, I guess around this time 18 months ago, when I went to this conference called SPP, the annual meeting of the Society for Philosophy and Psychology. And anyone been to SPP? Yeah? Okay, right, Josh. Cool. Well, it's a lovely conference. I encourage you all to go, though maybe not at the same time because you would double the attendance of the conference. It's really small. But at this conference, I had this like really lovely lunch with a lot of folks who build these kinds of. Actually, I'm noting that like Sarah Wu is in this picture, which is kind of funny. But we all had this lunch, and we kind of vented to each other for a while about the fact that this is just hard to do. Like writing these models is really difficult. And then we said, well, maybe we should do something about this. Maybe we should build some new kinds of tools that would make it easier to do this kind of science, easier to build these models. And we thought the right kind of tool to build would be a kind of programming language that's specialized for building these kinds of recursive reasoning models. And that's what turned into Memo. So Memo is a programming language that's designed for building these recursive reasoning models. And it's specialized for just doing that. So you can't do don't build a web server in Memo, but you can build all kinds of these recursive reasoning models in Memo. And Memo is designed to address the two problems that I talked about earlier. The way it addresses the correctness problem is it's not designed around sampling random variables. Instead, the entire language is architected around having agents who make choices. And so in Memo, you directly write words like believe, think, see, do, know, want, imagine, and you directly write down the model the way you think about it in your head, the way you would explain it to a friend at a bar. And I think that makes it a lot likelier that you're going to implement the correct model. The way Memo addresses the efficiency problem is to realize this kind of interesting fact about possibilities, which is that two possibilities are kind of necessarily independent. If either X could happen or Y could happen, then I should be able to reason about them in parallel. And today, computers are really, really good at reasoning in parallel. In fact, all a GPU is a machine for doing a lot of computations in parallel really fast. And so that's what Memo does. Memo compiles your model to run in parallel on GPUs or even CPUs. In fact, like Memo would run super fast on the hardware in this iPhone because today's hardware is just very good at parallelism in all sorts of ways. So Memo compiles to code that runs in parallel on GPUs or CPUs, and in this way can run a lot faster than code that's sequential. Okay, so I wanted to end this little introduction to Memo by giving you like a high-level vibes-only perspective on what it looks like to write Memo, and I wanted to do it by implementing the model I told you about earlier. So you guys remember this game? There's 3 things on the table, etc. Would someone please nod? Yeah, okay, excellent, thanks. Okay, so we're gonna implement this model in Memo in the next 7 minutes. So Memo lives inside Python. And so when you start implementing a model in Memo, you can actually just start writing Python code. So here, we want to start by just setting up the rules of the game. And the rules of the game are there are these 3 things on the table. Let's call them reference, borrowing some jargon from linguistics. There's these 4 words that the teacher is allowed to use, or the speaker is allowed to use. Let's call them utterances. And then, okay, someone needs to explain to Memo like which words correspond to which objects, right? Like the green square is green, but the green square is not pink. So you have to write down this little function that tells you whether an utterance U describes a referent R. Raise your hand if you feel confident that you can write this function in Python yourself. Okay, pretty good. Thanks, guys. Okay, once you've set up the rule of the game, then you can start writing some Memo code. Now, Memo, as I just explained, is fundamentally a language for doing things in parallel, but it's also in some ways a language for creating like tables of numbers in parallel, tables like spreadsheets. So in this case, for example, what do I mean by a table of numbers? I mean like the data table that I showed you from Ching and Franca. So a conditional probability table that says if I'm the listener and I hear the utterance U, then conditioned on U, what is the distribution of reference that I'm likely to pick? So that's the data table that we're going to generate, or that's the prediction of tables that we're going to, that's the table of predictions we're going to generate. And so the first thing we write in a memo model is just the axes of this table. It's going to be indexed by utterances and reference. Okay, so right. So how does this model go again? What did I tell you? I said there's a listener in this model, and the listener thinks there's a speaker. The speaker is given one of these three objects to communicate, and then the speaker chooses an utterance with which to communicate it, right? In memo, here's how you express all of that. You say there's a listener. The listener thinks there's a speaker, and the speaker is given one of these references to communicate, and then the speaker chooses one of these utterances in order to communicate it. So it's just like how you would intuitively think about how this model is set up. Okay, once you've set up the listener's model of the speaker, then we're almost done. It's the main event. The listener observes what the speaker chooses. The listener observes the utterance, and then the listener makes a bet. The listener says, well, which object do I think it is? I think it's that one. And that's it. The last thing we do is we return a distribution over the listener's referent. That's the whole model. And when we run it, as promised, we get out a data table. It's indexed by reference and utterances. So reference and utterances. And so, for example, we can read off that if the listener hears the word square, then they're 100% likely, according to this model, to say the green square, which, by the way, was borne out by your behavior, right? Like when I said green square, you all pointed to the green square. But if this model hears the word green, it predicts that people will be 50-50 between the green square and the green circle. Okay, so if you were following along so far, you might start to get a little concerned at this point, because the whole reason we started down this journey was the empirical observation that people have a preference for the green circle over the green square. Okay, so does anyone want to offer a theory of what's wrong with this model? Why is it predicting a 50-50 split between the green square and the green circle, as opposed to predicting a preference for the green circle over the green square? Does someone want to hazard a guess? It's fine, by the way, if it's not the right answer, but I'm curious what you think. Yeah. Yeah, go for it. Yeah.
Listener is thinking about the speaker, thinking about listener. The listener is just thinking the speaker is going to make the choice based on silent references and objects.
Yeah, that's exactly right. Thank you, Alex. So what Alex just said was, well, I said in this model that there's a listener and the listener thinks there's a speaker, but then I just stopped there. Whereas earlier in this talk, when I was introducing this model, I said, well, there's a listener, the listener thinks there's a speaker, but critically, the speaker is then recursively thinking about how the listener might act. And we just haven't done that yet, right? Like we're just missing these additional thought bubbles. Okay, at this point, you might start to feel a little concerned, right? Like, what are we going to do? Is Kartik now about to like add more lines of code and start saying, okay, listener thinks speaker, speaker thinks listener, speaker thinks listener thinks, like that's about to get a little bit out of hand. Like that, I don't know. But actually, it turns out that we can do something kind of slick and implement this fully recursive model with just not a lot of additional work. And let me show you what you need to change. Okay, so look up at the slide, because if you blink, you'll miss it. Here's what needs to change. Two things. Okay, thing number one, we have to add recursion to this model. So now the speaker doesn't choose you, let's say, just uniformly among the denotationally consistent utterances. Now the speaker chooses you based on some function of the model of the listener. We already have this model of the listener. We implemented L just now, and now we're going to recursively call L in our definition of L. So that's the recursion. And okay, fine. So if you have recursion, you have to make sure that you like count the number of levels of recursion so that you bottom out. Otherwise, there's a problem of infinite regress. So fine, we'll introduce this parameter. Oh yeah, absolutely. Okay, so recursion is a computer sciencey word for self-reference. Anything that has a reference to itself. So this picture is a picture of this like hot chocolate container or hot chocolate company, which I really like because it has within it this image of this woman who is serving hot chocolate, and next to it, she's holding the box, which, if you look really closely, you'll see has a picture of the woman holding the box, and it just goes on forever. And that's recursion. Recursion is self-reference. So in this model, the recursion is the fact that there's a speaker who's thinking about the listener, but then the listener kind of within their thought bubble has like a smaller version of the same picture. There's a speaker thinking about the listener, and then in the listener's thought bubble, there's a speaker thinking about the listener. Do you see how that's recursive, and do you see how that's just like the woman with the hot chocolate? Okay. Yeah. But like as a general you, like, would someone please like to nod to affirm? Okay, great. So that's what I mean by recursion here. And when I talk about levels of recursion, well, okay, so this hot chocolate situation can't go on forever, right? Like that just like logistically seems impossible. Eventually you have to stop. And the number of times you go deep, that's what I mean by the number of levels of recursion. And so the way this model is built is you say, well, I want a listener at 3 levels. The listener at 3 levels thinks about a listener at 2 levels, so t minus 1. And then the listener at 2 levels goes back and thinks about the listener at 1 level. And this goes on until you run out of levels. And then when you bottom out, you default to maybe a simpler listener who maybe just picks uniformly at random. Thank you for asking about that. Are there other questions about this? Yeah, Ben. It's literally because it would then run out of space on the slide, and I was hoping no one would notice. But yes, you do have to pass beta to the recursive call. No, it's all good. Eagle eyes. Any other questions? Yeah.
Referencing, but how would you implement something like your entire this? So do you need to have a parameter that's over the level K that should be specified here on the listener side, or?
Yeah, great. So the question is, in this model, you have to input the number of levels of recursion, right? I said, like, what if t is 3? Then you have like 3 hot chocolates. But you might want a richer model that says, well, I don't actually know what t is. Or maybe the speaker doesn't actually know what t is. Maybe the speaker has some uncertainty. You can build models like that. And the way you would do that is by thinking, by having a new random variable, which is t. It's the number of levels of recursion. And I can show you afterwards how to build that model. It's not too difficult. But that's a great question. Thank you. Okay, I'm going to move on now. The next thing, okay, so I said that there were 2 things you have to change. Thing number 1 is you have to add recursion. The second thing you have to do is make the speaker now like rational in some sense with respect to this recursive model. So, okay, if I say the words chooses with respect to a softmax, raise your hand if that's meaningful to you, and raise your hand if that's not meaningful to you. Okay, so what we're going to do is have the speaker choose with respect to a softmax over the probability that the listener guesses the right thing. And okay, so if you have a softmax, you guys seem already aware that you need to have some sort of free parameter that's the temperature or the sharpness of the softmax. That's this beta parameter. And so that's the second parameter to the model. So the model now has 2 parameters, the number of levels of recursion and the sharpness of the softmax. Okay, and if we run this model, let's say at t equals 1 and beta equals 1, indeed it predicts that people should have a preference for the green circle over the green square. Okay, so you might say, Kartik, great. So you spent like 1 slide explaining this model to us at the beginning of this talk, and now you spend 1 slide showing us this model, and it's a simple model, and it's simple code, and like, what am I supposed to take away from this? I think it would be valuable to compare this model to how you might implement it if you didn't have memo. So I actually found the original source code that that was used, or that Noah Goodman wrote to implement this model many years ago. And it's in R, and it's about 300 lines of R. And it's really hard to read. It's actually like a heroic effort, I think, that Noah did to implement this model. One of the reasons it's hard to read is that so much of this model is doing a lot of like really gnarly array index work, right? Because in this model, you have to manage a lot of tables of numbers, a lot of probability tables, and you have to keep track of like, is axis 0 the utterances or is axis 0 the reference? So a lot of this model, if you squint, you can see just a lot of like for loops occurring over arrays that you have to be really careful of managing. But also, it's just really easy to make an oopsie when programming this way. For example, it's really easy to just forget to normalize a distribution and then catch that error many, many days later when you're fitting to data. So I think this is like an amazing bit of code, but also like the amount of effort that went into implementing this model, I think is not commensurate with like the actual complexity of what this model is. But in comparison, here's the situation with the memo version that we just wrote together. Firstly, I think that this model matches our intuitive description of how you would like explain this model to a friend at a bar. I got this email from a memo user a few days ago, or I guess a few weeks ago, and he said, "Well, I've been using memo for a while, and it's kind of interesting. I keep getting these errors, which are annoying. But one thing I've realized is that these errors are actually valuable because each time I have a bug, I get an error message that tells me what the bug is, and it helps me refine my thinking about what the model is." So, Lio will tell you, will show you a couple of examples of how these error messages are helpful. But I just want you to, I guess, take away from this that writing models in this way that's kind of impedance matched to how we talk about them, I think really is valuable for correctness. Okay, it's also like out of the box about 10 times faster than any other implementation of this model that we could find on the internet. And if you were to plug in a GPU, it would be even faster, and you actually have to change 0 lines of code. It just immediately starts using the GPU. It's also end-to-end differentiable. So I told you that there was this data parameter, the softmax sharpness. If you wanted to fit that to data, you could do so by gradient descent or by parallelized grid search pretty much immediately in like 5 or 6 lines of code. And as you can see, you can then plot things using these libraries we know and love, like matplotlib. So here's some gradient descent with matplotlib. Actually, because there's this combination of being fast and being in the Python ecosystem, you can do a lot of like really slick things. Like, for example, here's a model that a computational psychiatrist made of teenage suicide risk that in just a few lines of code, he made it update live with sliders. So each time he moves that slider, the model is being recomputed live and plotted. And this is just such a great way to get like an intuition for what your model is doing and how it responds to parameters and how it behaves. And Lio will actually show you how to build this in about 3 lines of code in a few minutes. Okay, and then the last thing I want to tell you about is because Memo lives inside Python, you can integrate it with all kinds of things in the Python ecosystem, like, for example, the deep learning ecosystem in Python. So I'm going to very quickly show you a quick example of that if you guys are interested. Can I actually take a poll? Raise your hand if you're interested in learning about Memo and deep learning. Okay, everyone's interested. So I am going to take a couple minutes to talk about this. Okay, so anyone use the microwave recently? Yeah. Okay. So microwaves have these displays, right? And these displays have like a finite number of little segments. And by turning these segments on and off, you can make these numbers or letters. And well, I don't know. If you're anything like me, from time to time, you're like, what if I dropped out of my PhD and became the person whose job it was to design the fonts on the like microwave display, right? Like, and if you think that's frivolous, let me just try to convince you that this is a hard problem. Suppose I told you, like, how would you represent a bee on one of those 7-segment displays? Okay, so a bee, right? What is a bee? It looks like this. So what do? I turn on all 7 segments, except that looks like an 8, right? B looks just like 8, so you can't have that. So what do? Well, you do the lowercase b. Lowercase b looks like this, except something that looks like this, that looks like a 6. So what do? Well, maybe you do 6 differently. Maybe you put a serif on top of the 6, but that looks like a G. Okay, how do you do a G? Well, maybe you do a lowercase g, but notice that that looks like a 9. How do you do a 9? Well, maybe you do a 9 without a serif, so it looks like that, but that looks like a Q, and now you're screwed because there's no other way to do a Q. So it's a hard problem. And then it turns out there are other languages. So for example, the Russians had to invent a whole nother font for Cyrillic 7-segment displays. I've been trying to obtain one of these because I think this is just such a beautiful piece of technology. Anyway, okay, so I'm telling you all of this because, as some of you might have guessed, I think that the problem of designing a font for a 7-segment display is actually just like the problem with the green square and the green circle and the pink circle, in the sense that, okay, well, there's a speaker who's trying to communicate something, a digit or a letter. So the space of reference is not the 3 shapes, but rather 26 letters and 10 digits. And then the space of possible utterances is not these 4 words, green, pink, square, round. The space of utterances is the different ways you can configure a 7-segment display. So there's 7 segments. Each one could be on or off. So 2 to the 7 is 128. So instead of a 3x4 problem, it's a 128 by 36 problem. But conceptually, it kind of feels the same. The only catch is like, what is the literal level 0 listener? What is the listener that isn't doing any recursion? Well, firstly, it's not a listener, it's a viewer because it's looking. And instead of it being like cut and dry, what the pink circle is pink, but the green square is not pink, we can use something like a ResNet or a computer vision model to try to determine just by looking at the segment display what type of digit it is. Okay, so if you do that kind of naively with a level 0 speaker who isn't doing any recursive reasoning, you get a font that like if you squint looks kind of fine. Like for example, for 0, it does a thing that looks like a 0, and for 1, it does a thing that looks like a 1. But you get all of these like unhelpful collisions. So 0 looks like O, and 1 looks like L, and 2 looks like Z, and 9 looks like G, 6 looks like B, and K, which admittedly is a really hard one, looks like T. But if you do this kind of recursive reasoning, using exactly the same model I showed you earlier, except changing out the reference space and the utterance space and the denotation function for calling into a ResNet, then it does its best to disambiguate. And okay, so like it makes some artistic choices that I personally would not have made, but I think it does pretty well for what I think is fundamentally a hard problem. Okay, so that's one example of how you can use memo with deep learning. It's kind of a frivolous example, but hopefully it convinces you that you can just plug in a ResNet. You can just plug in a language model into memo and it'll just work. Another thing you can plug in, by the way, is physics simulators. There's a lot of those in Python. So if you're into like the theory of mind world, you might have seen tasks like this, right? So there's a little dude. The dude jumps over over something and then gets to the triangle. And the question is, was there a barrier or not? And people and even babies, which is the interesting part, think that there was probably a barrier, because if there wasn't a barrier, then why did it jump? It should have just gone straight. If you wanted to build a model of this, you need a little bit of physical reasoning. You need to be able to reason about the fact that the guy cannot pass through the barrier. And in Memo, it's just a few lines of code to use a physics simulator to actually determine, to set up this problem and simulate the physics, and then connect it to a model of intuitive psychology, and then be able to make these kinds of predictions that babies make. Okay. Cool, that was 8 minutes, not 4, but I think I'm doing okay. I wanted to end by just telling you a little bit about how people are actually using Memo out in the real world. So we've implemented a lot of Memo models by now. In this graph, what I'm showing you is each tick is a different model. The 5 on the left are like classic models from the literature, or like examples you'd find in a text box, in a textbook. The 3 models on the right, these are the first early adopters of Memo who had old models that they converted to Memo for various reasons. The height of the bar tells you on a log scale how much faster these models got in Memo. And typically they get like several orders of magnitude faster. And in all cases, you have to write a lot less code in order to get that speed up. How many of you have heard of an MDP, a Markov decision process? In Memo, you can implement a value iteration solver in about 11 lines of code. How many have heard of a POMDP? Okay, how many of you feel like you could write a POMDP solver in the next like 3 hours or so? Yeah, maybe Ben, maybe Victor. Okay, I asked Michael Kokender for this, and he seemed unconvinced that he could do it. In Memo, you can write a POMDP solver in about 15 lines of code, and it runs just about as fast as the one Michael Kokender wrote in Julia. Perhaps for this reason, a lot of people have started using Memo. I think this list is actually a little out of date. And a lot of papers have been published that are using Memo, and more papers get published every month. So this list is also out of date. But yeah, hopefully, if you found any of this interesting, then you can be one of the institutions and one of the papers on the slide. That's all I wanted to say about Memo. I will pause for any urgent questions, but I will also say we're about to take a 5-minute break, during which you're welcome to come up and ask me questions. After the 5-minute break, Lio will come up and teach you in detail how Memo syntax works. Great. Yeah, question?
Yeah,
Yeah. It seems like I put it in a dangerous place. Oh, fantastic.
Or I would actually split a pair with you.
Oh, okay. Well, I'm not gonna eat right now, so
Oh, okay. In that case,
you should have
hang
a
on to it. I will have a
It's
whole.
like a talismanic Kit Kat.
Yeah,
It reminds me where I'm going.
it's a
and-
good luck Kit Kat.
Okay, welcome back, everybody. Can I see a quick show of hands? Is everybody actually, or yeah, who here is able to and wants to follow along with the Colab notebook and has been able to pull it up online? And is it running? Because the internet is a little bit weird. Okay, so before we get started, what are we trying to do here? Well, I'm going to have you guys go ahead, and if you don't know how to, if you've never used Colab before, you can run every cell by clicking on it and then typing in, at least on an English language keyboard, Shift Return or Shift Enter at the same time. So if I did that right there, it'll go ahead and install memo. You can also click play. There's like a tiny little play button beside all the cells, but this is a little bit faster. So go ahead and install both of these lines, the memo lang one and matplotlib, and raise your hand if you can't get that working, because that will make the rest of this a lot less fun. Cool. Okay, so just a little bit of an overview of like, what could you want to get out of a session like this where we're like making you live code along with us? I think the like most exciting thing that you could come away from a session like this is, I know everybody here has different research programs. You all work on social reasoning and social intelligence in some ways. People work on collective intelligence, social learning, animal reasoning, humans reasoning about animals, animals reasoning about people. And so really the goal, I think, from that taste of memo that Kartik just gave and of this session today is for you to walk away with enough of an intuition about how this language works and the kinds of models it's able to build, that you have some sense, either A, of how you might be able to express models you are interested in building in a language like this, or B, because the developers of this language are literally just here. They're just people, they're students. Things that either are not well captured about your model that you're interested, kind of like the question that was just asked, or features, right? As you'll see, a lot of memo looks like saying something about what an agent does or thinks or imagines or wants. I was just talking with Kartik yesterday about what an agent wishes and how wishing is different from wanting. And so if there are other verbs like that express things that agents that you are interested in modeling feel or are thinking, that is like a very live place here in the summer school for you to express like, okay, how would I either do this, or is this something that's just not captured in this language that we want to model? And so, that's kind of this is not just a lesson. This is us showing you how this thing works so that you can say how you wish it would work, how you want it to work. So before we get started, how many people here actually have, just for the sake of like how slow we're going to go, used NumPy in Python? Can I just get a show of hands? Okay, so almost everybody here. If you haven't, I think the easiest way, I'm almost sure that everybody put up their hand, but if you have only used it a little bit or you mostly use R, pandas, or another data table, I think the easiest way to think about what NumPy is a series of tables that are exactly like the data frame that you would pull up in Excel, right? They're just tables of numbers. They often have axes. They can be one-dimensional. They can be two-dimensional. They can be many-dimensional. And so why don't you go ahead and, if you have this and want to follow along with me, if you run this code right here, what you should see is, here, let me just type this.
The floating.
Let me just type this. This meaning controls. Okay, cool. So we're basically just initializing an array. It's an array called A, and in Jupyter Notebooks, which I think many of you have seen before, running any kind of code cell will show the output of the last line below it. And so we've just created ourselves a tiny little array of 3 numbers. It's one-dimensional, and they're just kind of a list. You can keep visualizing an Excel spreadsheet with 1, 2, 3. Why am I showing you this? Well, as Kartik mentioned, memo is really about, it's what its bread and butter is about building models of agents who think about other agents. But at the nitty-gritty level, one of the things that makes memo practically useful is it is building models that fundamentally are returning kinds of tables of information. And one of the most useful kinds of tables of information that it's usually returning are given some set of inputs or choices that an agent could make. So possible actions, that was like possible words that they could be talking about, or possible objects that they could be referring to. We're going to return you some bit of information about every cell in that table, like the probability that given this was their object they wanted to talk about and the word they wanted to use, that they would have used that particular word. And so I just wanted to kind of build up to that by showing a little bit of this kind of very granular syntax for those of you who haven't seen it before. And in NumPy, one of the core operations when you have a table of numbers like these, like this array from 1, 2, 3, is that you can apply operations that look like these kinds of point-wise operations, so a plus 1, that are actually going to be applied to every single number in that cell. So if I take this array 1, 2, and 3, and I just add 1 to it, like this in Python, that will give you 2, 3, and 4, because that operation has been applied to every number in that cell. And as you'll see, the way that memo models often work is you're defining a series of operations that are essentially like point-wise operations like these. They're going to be applied to every number. Similarly, if I have a two-dimensional array like this, so the first line is 1, 2, 3, 4, 5, 6, and I multiply that whole array point-wise by 2, you've probably seen this before. Now every single number in that array is doubled. Okay, so we're just about to get ready. We're going to import memo. So you always write this from memo import memo line. And so let's give ourselves something to write memo models about. Here we're initializing an array called n. And this numpy.arange 1 through 11 is just initializing a list of numbers that starts at 1 and counts up to the last number exclusive. So this has given me an array of numbers 1 through 10, and that's what n is. And so now let's start writing a very simple memo model that will kind of just give you a sense of what that syntax looks like. So I'm going to run through this twice, because I think this will all be a lot easier to understand with access to actual agents. But what is a memo model? So every memo model is initialized by using this little @ symbol, which is a decorator, something that tells you that everything in the function to follow is essentially importing memo. It's going to be running in memo. And it's a definition of a model. And what this syntax here is showing you is, as Kartik kind of breezed through, the axes of the array to be computed. So what does that mean here? It's saying that everything that's going to happen inside this function is really going to run over every single item, _n. So I'll always use that little underscore to indicate the particular variable that I'm querying in a list of objects over some list or some array. In this case, it's my list of numbers n. So this is a function, and it's going to be run for every single number in that list of numbers. And this is going to do something when I run it that is almost exactly like what I wrote up here with my broadcasting operation, right? We are going to return some expression that is applied to every single value in those axes. And when I run that model, well, indeed, I can see that for every single, we ran this over every single number, my list of numbers 1 through 10, and I added 1 to it. Is everybody, does that make sense? And also, obviously, it doesn't make sense. Feel free to ask a question. As kind of was mentioned briefly earlier, one of the useful things about this language is it's essentially built to extend Python, and specifically to extend this library called JAX, which is a library for writing very fast operations over arrays of numbers. And that's really useful because that means this language doesn't need to implement most of the things that you might actually want to do with your arrays. Anything that you can really do in NumPy or SciPy, whether you want to have access to various functions like your standard logs, cosines, exponents, etc., you can just directly import those and expect to be able to use them in the body of your languages. So if I didn't want to add one to every number in this list, but I rather want to take the log or take the exponent, I can just do that directly. And so now here's a model that takes in numbers 1 through 10, and is applying the log directly to it. And so these are the outputs of that model. And as you can see, what's happening here, when I call my model, you can always pass in this kind of hidden parameter. You can pass in this parameter print table equals true, and that's what's giving you this kind of nice tabular notation to actually see and inspect what you're doing. Okay, is everybody with me so far? Cool. Okay, so now we're going to get to the bread and butter of actually what we would want to do with a model like these. And I want to just take a moment to talk a little bit more how a memo model actually works. So usually, we're writing a model that is not just trying to do some kind of operation to everything in an array, but actually to talk about an agent. And most memo models, the way that the syntax is written is designed to make it easier for you to think about when you were to describe, what am I trying to model here? What are agents doing? Well, usually we're talking about agents who are doing one of several verbs, right? We're talking about agents who are choosing to do something in the world, or who knows something, or have seen something. And so the basic syntax of a model like this is almost like you are writing lines of a script of a play, where you're declaratively naming an agent like Alice and using one of these verbs that memo defines to say what exactly those agents are doing. And where that gets interesting, of course, is when the things that they are doing are reasoning about other agents that you're talking about here. So we're going to introduce one of the verbs that is really kind of the most fundamental bread and butter of these kinds of models, and that is the notion of choosing. And so let's imagine an agent who wants to choose a number from our list of 10 numbers, 1 through 10. So we're going to write an expression with our agent named Alice. We're going to say that she's choosing something. And what does it mean to choose? Well, this syntax is saying for some set of actions in a set of possible actions. So for every possible number that Alice could choose, in this larger list n, we're going to define the prior with which she tends to choose that number. And so this WPP refers to with probability proportion to. And if we say, well, Alice has no particular opinion about any of these numbers, she has a uniform distribution, what is the probability that she is going to pick any one of these numbers? It's 1 in 10, right? And so we can write down with probability 1 in 10. And if we want to print that out and ask for the probability, that's this PR in brackets, that the number that Alice has chosen, alice.n, is equal to one particular number I'm asking about, well, we can see something that looks exactly what we'd expect, right? For every single number, she has exactly the same probability of choosing it. So I just want to break down a little bit of what's going on here. What is this actually saying in more granular detail? Or what is happening when you have Alice choose something? Whenever an agent makes a choice, we say that these variables n become something that only this particular agent has access to, right? Only Alice knows about the choices that she's internally making. And so when we call this alice.n, we're referring to the choice that Alice herself has made. Whereas when we refer to this underscored n, this is me asking you, the person who's modeling this, whether that number that Alice has chosen is the number that she herself knows about. One of the really useful ways that that memo attempts to avoid a common class of bugs, if you've ever written a model like this, you know that it's really easy to kind of forget to normalize, right? And so throughout the rest of this talk, whenever memo actually has an agent produce a distribution over something, like a choice over a set of actions, we can have this with probability proportional to, wow, I wish I could stop doing that. We can have this with probability proportion to automatically normalize over all the possible choices that you've specified. And so if I were to run this again and just say with probability proportion to 1 assigned to every one of these, that's an easy shorthand for providing a uniform distribution. And in general, for the rest of the syntax I'll show, everything will kind of be automatically normalized in that way. Any questions about what is going on here so far?
Actually, just a quick question, why, like numerically, this is like a bit bigger than 10, 1 over 10?
Yeah, so I suspect that that's actually just a quirk of floating point arithmetic
Yeah,
as it's implemented in
yeah.
JAX arrays.
So this is Jackson.
Yeah, yeah. Okay, so for everybody who actually hopes to work on a memo model with me later, I just wanted to walk through a couple of useful tools for debugging when the memo model that you've written goes wrong. And this is related to what Kartik was saying before. So I think there are kinds of two classes of errors that you can run into when you're running models right here. One of these are kind of errors where you've run into some basic problem of the syntax. And one really, here, let me just make it even more. Right, an even dumber error. So let's say that instead of trying to return the choice that Alice actually made, and you accidentally mistype the name of a variable and a choice that she made, you call alice.m. One kind of common class of errors that you can see down here in that it's printing out is saying, trying to tell you really verbosely, trying to walk you through really verbosely what might have gone wrong here. So it says, Alice is not yet aware of any choice that she has made. And I think that's actually kind of a subtle but useful error, right? It's either that you've called something wrong, like, I'm mentally choosing a number n, you're asking me what m is. I said, well, I have no idea what m is. I didn't choose that yet. Oh, I see. I think these are switched. Another subtler class of error that I want to just point out here that memo can draw your attention to is when there's actually something that is sort of formally wrong about the model that you've written that doesn't make sense. And I think these kinds of errors aren't just annoying, they're useful because they make you get more precise about what you actually mean. So let's say that I said that Alice closed her eyes and she chose some number, and you're asking me whether Alice's particular number was 1, 2, 3, 4, 5, or 6, or 10. Well, basically the answer to that is, I don't know, right? Like only Alice knows the answer to that question. That's why we had to write that probability sign. I can only tell you the probability and how uncertain or certain I am. And so this is another kind of common error message you can see. It's trying to subtly nudge you to ask whether you in some way have forgotten to include the source of uncertainty in your calls. Did you mean to use an expectation or a probability in the return statement here? And I think that these kinds of errors, annoying as they may be, are actually quite useful because they help you locate the sources of uncertainty in a model like this. Okay, so let's say that Alice actually has some kinds of opinions about something, right? She's not just wantonly choosing numbers at random from this list, but she actually has some kinds of preferences. Well, one way that we can encode this basic sentiment is to say that, well, Alice has some kind of internal utility function that is defined over the values of the numbers at hand. And there are many different utilities that Alice can have, but let's say that Alice is somebody who loves even numbers. She has a high utility for numbers that are even, that mod 2 and return 0, and she otherwise has 0 utility. She has no use for any odd number. In general, this pattern where we define a utility function over some kind of set of choices that we make is one that I think is common to most of the models that you can write. And one tiny bit of syntax that I want to just call your attention to here is, as I said, memo models can call anything else that you can define in Python. However, to be able to get access to that kind of speed up that we mentioned, any kind of function that you call outside of or define outside the body of a memo model needs to be decorated with this little thing that says @jax.jit, which is just telling your model that this is a JAX function, something that is running over arrays. So we've defined this utility function here, and one thing to just draw your attention to is, okay, so Alice is now choosing a number from this list with probability proportional to her utility. We're going to add in that exponent to make that a softmax. She has generally a preference for even numbers, but she doesn't have to choose even numbers. And now when I print out the probability that Alice will choose any particular number, you can see that this is behaving essentially as we expect. If the numbers are odd, she prefers them much less. If the numbers are even, she prefers them much more. Charlie, did you have a question?
Yeah, I just wanted to ask, maybe you could explain what JIT stands for?
I think JIT means just in time, which means that it'll only be called right when you call this. Okay. Any questions now? Okay. If you do have questions, I'll say, do feel free to call them out, because most of them, as I said, will have to do with, I think, subtleties of how the language works or maybe isn't working for you. Okay, so one really useful utility, we can all sit here and kind of like squint at this table of numbers and basically say that it's behaving according to what we expect. But of course, it would be much easier if we could just sort of pipe that all automatically into a plotting function, which you can do. And so now if I look at all the different possible numbers, we can say, okay, yes, this is looking basically as I want. Alice has a preference for even numbers, and that preference is much lower for odd numbers. But of course, we might say, okay, is this like really what if I said, yeah, Alice is a person who likes even numbers and hates odd numbers, like you might say, okay, well, what kind of a person is Alice? Is she someone who absolutely won't stand for even numbers? Is this about like numbering houses where I literally need to have the even numbers on one side of the street? And so if she said, hand me an even number and you handed me an odd number, I'd be like, that is absolutely wrong. Or is it just like, we're playing a game, I basically said, give me something even, and if you give me something odd, I'd be like, yeah, whatever. That kind of parameter is, the kind of parameter that we are fitting in our models all the time. And so in a function like this, memo subtly distinguishes between values that are absolutely fundamental to the model, that is what is appearing in square brackets over here in the axes, and things that are parameters that are the kind of parameters that you might fit. And so for those who are, this is the beta parameter in that softmax distribution that we mentioned earlier. It expresses how strongly how close to an actual maximum over particular preferences you actually feel. And so if we now change this line of code just subtly to say, okay, she generally has this utility over different numbers with this amount of sharpness, we can see that for different values of beta, and you can go ahead and type in whatever value of beta you might wish, we are making that preference for strong numbers sharper and less sharp, to the point where if I make beta relatively sharp, basically she will never choose an odd number. And I think one of the most useful aspects of this plotting function, and this was something that was really briefly touched on before, is that you can use the full library of IPython widgets, these kinds of interactive widgets, to make visualizations that I think are actually really helpful for debugging a model like this. It's kind of silly to apply it to this like very small setting where it's all about Alice choosing numbers. But if you look, this is actually expressing kind of exactly what I said, right? As beta gets bigger and bigger, her preference towards the even numbers is getting sharper and sharper and sharper, and I can see her desire to pick anything odd falling away. If I push it in the other direction, indeed, if I push it down to 0, I can say, well, this was a loose preference at anything. I've essentially recovered that uniform distribution. And of course, you can give yourself access to the full set of bells and whistles that these kinds of widgets might encode. Okay. Let's get way more interesting than somebody choosing numbers alone in a vacuum by themselves. Let's talk about agents who know something about the world and are thinking something about other agents. Okay, so let's stop talking about Alice. Let's talk about Alice's friend or enemy. We'll talk about Bob. I was talking to somebody yesterday about mental states, and they were like, what is a mental state? Why do we even have these? And part of the reason, I think, or the kind of idea that Memo makes explicit, is this idea that we aren't, all we can ever see is like the outside of the people in front of us. And so all I can ever be as Bob, thinking about my friend Alice, is I can introspect on my perspective of what is going on inside Alice's head, but never anything more. And that is really what this secondary level of reference is meant to encode. From Bob's perspective, well, let's say that Bob is the person in this study who is being shown every single number _n, and I'm asking you whether, I'm asking you, Bob, is this the number that you think Alice would have chosen? Well, we can encode that very straightforwardly and kind of directly as you said it. by introducing this thinks operator. So I'm saying here, what does Bob know? Bob knows one thing. Bob knows precisely the number that you've asked me. What does Bob think about Alice? Well, what Bob thinks about Alice, based on the description that you've given here, is exactly the thing that you and I in this room have already just been told. And so, as you can see, this line, Alice chooses one of the numbers in n with probability proportional to that softmax over that preference for even numbers. We can take that line of code and stick it directly within the square brackets of this operation, thanks. And what this is encoding, just to kind of push that and nail that down a little bit further, is nothing about is distant from the real Alice in the world. Actually, this memo model is encoding simply the fictional idea that inside Bob's head, there is an agent named Alice. And as far as Bob is concerned, the way that Alice is choosing numbers is with a preference for those that are even. And that's really useful, as Kartik mentioned, because a lot of, I think, the bread and butter of what we are studying here are cases where somebody's belief starts to diverge from what is actually true in the world, right? This is what Bob thinks. For all we know, Alice could have her own particular preferences. And I could actually write that down, right? If I were to say that Alice chooses n and n, the real Alice, right? And give her her own utility function where actually like odd numbers are key. We can have a function here that expresses the difference between what the true Alice in the world actually wants and what the Alice of Bob's sort of idealized imagination really desires. And in fact, we could return all kinds of expressions like, what is the probability that Bob is going to get it right? And Bob will actually be wrong every single time. But for now, we're just going to let Bob live inside his own particular dreams. And so breaking down this return statement here, I just want to walk through the syntax because I think it's short but subtle. This is saying, tell me what in Bob's mind, so the way that square brackets work in memo, they always step you inside an agent's frame of mind or frame of reference. So in Bob's frame of reference, what is his particular probability that the Alice in his head is going to choose a number n that is the number that you are asking about, number that he's been shown. And so from Bob's perspective, this is now showing me probabilities that are exactly the ones that Alice had in mind. But the important distinction here is that this is just Bob's belief about what's going on. Does that make sense? Any questions about how this would pertain to models that you guys are thinking about right now?
This is just a really tiny minor thing, but like I'm really wondering. So in the when you set the beta equals to 0, then the belief is comes to be just identical, like a home distribution, and then probability says not exactly 0.1 and some floating number. Is that okay, or is that like could be a source of issues later, like when you want to care about like, exactly. Whether this is exactly 0.1 or something.
Yeah, I think that the only place that could come up is if you are enforcing, or like in general, when you are using floating point arithmetic, yeah, a quirk of NumPy arrays is that you always generally want to ask about these kind of comparators or sort of like noisy comparators, just because like in true probability space, if these are continuous probabilities, you can never actually ask whether someone's probability is like exactly anything, right? The like amount of support on that would be nothing. And so in some ways, this is unintentionally enforcing that. I think in practice, it means that, yeah, you shouldn't really be asking about probabilities, whether a probability is exactly some number. But that's actually true in general. You should be asking whether a probability falls in some range. I don't know if there are any other things you want to say about floating point arithmetic.
Oh, yeah, I guess. So one thing I'll say is, anytime you type 0.1 into even regular Python or R, it's actually secretly 0.1000017. And the software is usually smart enough to show you just 0.1 because it knows that probably that's what you want to see. But the memo table display is not that smart. And so it shows you the like extra bit of like interest on top of that, but it's actually the same 0.1 as you would see anywhere else. So it's just as precise as anything else you would do. The other thing I'll say is if you really, really care about that extra bit of change, there's an option to use instead of 32-bit precision floating point numbers, 64-bit precision floating point numbers, which are not just twice as precise, I guess, but like a factor of 2 to the 32 more precise. But I have yet to come across anyone who needs that level of precision for their modeling efforts.
Yeah, I think it's fine to have this like limited precision for each number. I remember like because like we want all sum of all the number goes to 1.
Yeah.
So is this information stored somewhere? Like, or no, we cannot show exactly 2.1 for everything, but can Python somehow know that, but there's still some of that.
Yeah, so it does know that the sum of those numbers is 1 up to machine precision. And even if the numbers in the table seem a little off and they don't seem to add up to 1, like up to machine precision, they do. Or, you know, if you were to type in Python like 0.1 plus 0.1 plus, like that will also give you 1. It'll give you the same 1 as what you'll get out of memo, but it will be printed as 1 because Python is smart enough to know that you don't care about the extra change on top. And actually in Python, I think sometimes it doesn't work. So I think it's like if you type 0.1 plus 0.2 or something, sometimes it'll print out 0.30004. Or that might not be exactly the right one, but there are some cases where the floating point is just very easy to expose. So actually this level of like imprecision is just like latent in all computation you do on your computer, but it like leaks out when you have this like poorly written table formatting routine that I wrote one night.
Yeah, I think one last thing to say about that, and that actually goes back to like, what are we talking about when we are using any of these numbers here? Why are we using these kinds of like higher order constructs that give us access to what we meant when we assigned that probability is, you know, if you were to go to, or like a lot of times when we're asking why these things sum to 1 is because fundamentally we know that these are objects in a distribution. That's why we care about them. And so another way that you can manipulate all of those objects here, right, is by directly calling their values with respect to the agent. I don't have to do the normalization myself. That's one of the things that we've shown. But also, if I'm like asking for these individual components that I know should sum to 1, I can reference them over the original arrays that they stemmed from. And so part of the like, I think, impetus behind preventing bugs that actually come from me referencing numbers when what I actually want to talk about are mental objects and mental states, like preferences over different choices that I know should sum to 1 mathematically, is by giving you direct access to those objects that I think are the things that we want to be talking about in our model most of the time. Like, right, I can, yeah, kind of work together with different sets of preferences that agents have and beliefs that they have, and just expect that those things should continue to sum up exactly as correctly, because in the real world, where, you know, I don't think that our minds are doing that kind of normalization except very subtly under the hood, that's not really the kind of object that we would think about. Okay, we're almost at the end. I'm going to, you know, have Bob now make choices that depend on Bob's fictional simulation of what he thinks that Alice should do. I think that you can see this has a lot to do with that kind of reference game, the communicative game that we showed earlier, and then we'll be at the end. Okay, so yeah, Bob has in his mind an imaginary hypothetical picture of an Alice who's choosing even numbers. And let's say that Bob wants to deliberately make choices that depend on what he thinks Alice is going to do in some way, like choose a different number than Alice every single time. Well, we can write that down, again, in this kind of like declarative syntax by saying, okay, well, when Bob considers any particular number in this list, he's going to choose them or tend to choose them with a probability that his number is not the number that he thinks Alice would pick. And again, you know, this is not referring to a real Alice in the world. These square brackets refer to this is something that is happening inside Bob's mind. So when he is considering this number to choose, he's considering his particular imagination of Alice and choosing that accordingly. And so if we can see the probability now that Bob is going to choose a particular number, we can see that he is placing his mass on the odd numbers, as I would expect. And bringing it back to that kind of false belief that I mentioned earlier, right? we could again have an actual Alice in the world choosing numbers accordingly, and that would make no difference to or that would not directly intervene on what Bob's picture of Alice is going to be. Does that make sense? Okay, so the last verb that I want to introduce here, and then you'll really kind of have, I think, a full toolkit of things that agents basically can do in the world is, let's say that Bob now actually sees something. For example, Bob sees that the particular number that Alice actually chose was this number k. Well, so just before we run this, what are we going to expect? So if I said like Bob's ultimate goal is to just choose whatever number Alice hasn't chosen, Bob initially expects that Alice is going to choose even numbers, but it turns out that Alice chose 3. At that point, Bob doesn't care, right? He should say, okay, I can choose any other number because I already know what Alice has picked. And if we run this function that we have updated to include this observes, we can see that is exactly what's happened. If Alice chose 3, we can see that the only number he doesn't want to choose is the number 3, and so on and so forth. And to just walk through that observes sentence a little bit more slowly, observes, if you've ever written a Bayesian model that conditions on something, observes functions essentially like a condition statement, and the particular syntax that it uses is we have an agent who observes something. What do they observe? Well, they observe a particular choice. And what is that choice? We always usually want to be comparing that to some kind of random variable that exists in the world. And so what always follows this is statement is the name of some kind of variable that exists in the world. Again, I think this table is kind of difficult to read. It basically encodes that idea, but you kind of have to like squint to see it. The pattern that you're looking at doesn't really leap out here. And so as with before, something that I think is just particularly helpful is since these are all just arrays, we can pass them into any array plotting function. And so I think what makes it a lot clearer what's going on here is the notion that Bob is just placing none of his probability mass on the particular number that Alice has chosen, and everything else uniformly over everything else. Okay, so through this very toy example, what have we done here? Well, we've introduced, I think, 3 different fundamental verbs that are just the basic bread and butter of what it means to write models, right? We've introduced the notion of models that are indexed over arrays of choices, the idea that you can have different agents, and agents that are able to do a number of things. They're able to make choices over some set of actions with respect to some kind of probability. Something I didn't introduce here that is fundamental to the MDPs and POMDPs that Kartik mentioned is that in addition to choosing actions sort of sloppily at random, there is also the option to change this with probability to something like to maximize or to minimize with respect to some utility. So agents that make choices. Those choices could be wholly dependent on things in the world, or they could depend on other agents. And when they depend on other agents, at the end of the day, the only way that we can know about other agents and what they plan to do is either by directly observing something that they've already done, so I can observe somebody else and then choose my choice accordingly, or by what I think that they will do. And what an agent thinks that another agent will do is simply sort of taking that script of the play that is unfolding here and pushing that inwards inside the frame of reference of any particular agent. And so I think hopefully what I've shown that's the most useful here is I can take all of these statements about particular agents and nest them inside the head of another agent to have mentally that kind of internal reference to other agents, and that's where we can get that kind of rich recursive reasoning behavior that Kartik mentioned, where the things that I might be thinking about include agents who are themselves thinking about other agents, knowing about other things. Okay, that concludes our walkthrough. Are there any more general questions about Memo that either I can answer or that Kartik can answer while he's here? Otherwise, you can feel free to find us right after this. And if you're interested in applying this to your own projects or learning more about how that emotions model that I showed is built to join us for the group project, please do come find us after this. Thank you.